Miles and you.
You were.
Miles is closing everything.
Everyone's
That's
here.
right.
No.
What is that?
I need
There were three. I was.
I feel like if I get to play front row,
three types of people.
I think
Eliana,
if I stay front row,
biomedical
we might have a shot.
X
All right, let's get started. Professor Bridgman is traveling, and she's traveling for an academic conference. So I will give the lecture today. I'm the teacher assistant of this course, and my name is Pinchen Jian. I wrote my name on the right corner of this slide. So good afternoon, everyone. Let's first review what we learned from the last lecture. I think the key takeaways from the last lecture is that we got the Bode plot of some basic transfer functions. The first transfer function is s to the power of n. And that is we have 0 roots repeated by n times. For the magnitude plot, it will be a slope increasing by 20 n decibel per decade. And so the breaking point is 10 to the power of minus 1, 10 to the power of 0, which is 1, and 10 and 10. For the phase plot, it is a flat line, and the phase will always be the 90 degrees plus n. So if the n is 1, it will be 90 degrees. That is what you have from the last lecture. The second basic transfer function is you have real poles or real zeros. The form is 1 plus tau times s to the power of n. And you have a flat line at the beginning, then you have a slope. The breakpoint or the corner point is 1 over tau. And after this breakpoint, you got the magnitude increasing by 20 n per decade. And for the phase plot, you have a flat line, then you got a slope, then you go to another flat line. The break point is the 10 to the power of minus 1 divided by tau, and 10 divided by tau. And the phase increases from 0 degree to 90 n degree. The last basic transfer function we learned is the complex conjugate rules. So inside this thing, you got the complex conjugate rules, and you have the power to the power of n, which is repeated by n times. So according to what we learned last lecture, it looks like the real roots, but the slope is more steep. In each decade, the magnitude increased by 40 n decibel instead of 20 n decibel. And for the phase, it also looks like the real roots, real poles or real roots, real zeros, but it is increases by 180 times n degree instead of 90 times n degree. And I believe Professor Bridgman have very detailed explanation of how these plots are generated. And I just want to remind that these plots only tell you an approximate trend of how the magnitude and the phase will change. It is not an accurate curves. If you want the accurate curves, you need to use the MATLAB. But although these plots are not accurate, it tells you enough information about the breakpoints, corner points, and the trend of the variant of magnitude and phase. Like we said, all models are wrong, but some are useful. These models are very useful. The previous slide shows the plots of the basic zeros. Now we have the plots of basic poles. If you compare these two, you find that they look very similar. The only difference is that you inverse them upside down. That is because for the poles, you have the roots on the denominator now. So you always have a negative things on the powers. That's why all the plots are inversed upside down. So I'm not gonna go through all the details of the pools. I just try to review what we learned from the last lectures. Okay, great. Any question about these two slides? Great. Let's move on to the new things that we are gonna talk today. The first thing is, since we learned all the basic plots, basic Bode plots of the transfer function in the last lecture, now how to deal with the complicated transfer function, which has a form nominator divided by the denominator. All right, the first step is to factorize them. So we have GS equals to GKS multiplying with each other, K from 1 to L. And the denominator is K from 1 to P, GKS. So that's the first step. You want to get the basic transfer function from this complicated transfer function. Like you factorize them in a long series of things multiplying each other. So the GKS are the basic transfer functions. What means basic? Basic means what we see from the last two slides. The constant value, the real poles, the real roots, and the complex conjugate roots. These three are what we call basic. Okay, good. The second step is we want to group the poles and zeros together when they are the same. Like we learn how to deal with repeated zeros, repeated poles. So when you factorize them out, you find some zeros are the same, or you find some poles are the same, you group them together. Yes, you group the repetitions of a pole or zero or complex conjugate pairs. The third step is you need to draw a sketch for each pole and zeros, just like what we did for the basic transfer functions. And you just need it to be enough details, to have enough details. To see breakpoints and slopes. After you draw the sketches of those basic transfer functions, the next step is you need to prepare the omega axis. That is to say, what should be the range of the omega axis that I need so the plot can be presented in a clear way. To do this, you need to distribute all breakpoints of GKs and choose axis limit. Okay, after you prepare the omega axis, you know what should be the range of the omega I need. The last step is to fill in the magnitude and phase one band at a time. So what means band? I think just Professor Bridgman want to use this word. Then I have to explain what is band. The band, like each band is the interval of frequencies between a pair of breakpoints. All right, that's the 5 steps we do when we've made a complicated Bode plots. And let's do an example about using these 5 steps to solve a real question. Here is our transfer function. The GS equals to square root of 10 times S plus 100 divided by S plus 0.01. The first thing we want to do is we want to make the form of this transfer function to the form that we met in the standard simple transfer functions. So we need to clean it a little bit. This is the square root of 10. What is the standard form of this thing? The standard form is GKS equals to tau S plus 1. This is the standard form we use in the previous simple transfer function. We want to make this numerator and denominator into that form. So we factor out an 100 from the numerator, and we get S divided by 100 plus 1. That is in the numerator. And for the denominator, to get that form, tau S plus 1, we factor out the 1 over 100. And we get 100S plus 1. And to make these things easier for future calculations, we can have the first constant, those 3 things multiplying and dividing each other, is 10 to the power of 4.5. And the denominator is 10 to the power of minus 2s plus 1. And the denominator is 10 to the power of 2s plus 1. Okay, great. Then we get the forms we need for our future steps. And the first step is factorize. But we don't need to factorize anything. This is a very simple transfer function. We already got the form we need. So this step is done. The second step is group poles and zeros. But we don't have any repeated poles and zeros. They are just single poles, single zeros. So this step is done. Okay, the next step is we need to draw sketches for each pole and zeros. So what we have here is 3 basic transfer functions. This is the G1. It is a constant, 10 to the power of 4.5. This is the G2. It has a real zero, which is minus 100. This is G3. It has a real pole, which is minus 0.01. Okay, for the G1, what is the Bode plot of G1? Constant number. The magnitude is 20 times log 10 to the power of 4.5, which is equals to, which is equals to 20 times 4.5, that is 90. So the magnitude of G1 is 90 here. And it is a flat line without any changes, no matter what omega you have. And the phase for a constant number is always 0. So here we got the Bode plot of the G1. Now let's take a look about G2, 10 to the power of minus 2 times s plus 1. What is the Bode plot? Let's go back to check our basic Bode plot. It should have the shape in the middle, like a flat line and a slope. We just need to calculate the breakpoints. For the breakpoints, in the middle should be the 1 over tau, which is, the tau here is 10 to the power of minus 2, so it is 10 to the power of 2. So then 1 decade above it should be 10 to the power of 3. Oh, sorry about that. 10 to the power of 3. And 1 decade below it should be 10 to the power of 1. Okay, and what's the magnitude for the flat line part? It should be 0. And so it keeps being 0 until the breakpoint in the middle. Then it goes up at 20 decibel per decade. So after 1 decade, it should goes up to 20 decibel. So that is the magnitude plot of the G2. Now we get the phase plot of the G2. We still have the breakpoints 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. The starting phase, when omega is very small, should be 0 degree. And the final phase should be 90 degree, according to the basic transfer function we see in the previous slides. Then there is a slope from the first breakpoint to the third breakpoint, connecting to the 0 to 90 degrees. But pay attention to this. In real Bode plot, it's not a slope. It's not a straight line. It's some curves, but we just make it to be simple. And for the G3, you have poles. So it will be something like the middle, but it's all upside down. The breakpoint here is 1 over tau. It should be 10 to the power of minus 2. 1 decade above is 10 to the power of minus 1, and here is 10 to the power of minus 3. The starting magnitude should be 0, and it goes until the middle breakpoint. Then it decreases 20 decibel per decade. So at this point, it should be minus 20 decibel. So here is the magnitude plot of G3. For the phase plot, it is the upside down version of the middle one. The breakpoint is still 10 to the power of minus 3, 10 to the power of minus 2, 10 to the power of minus 1. It starts from 0 degree, and it finally will be minus 90 degree. And there's a slope in the middle. So this slope is just not straight enough. Sorry about that. And for the photo, Any question about this 6 plots of G1, G2, and G3? All right, great. Then let's move on. When we have those G1, G2, and G3, we want to get the final Bode plot of this entire transfer function. But to do this, we need to prepare our omega axis. How to prepare it? Basically, we need to see what's the breakpoints on the magnitude and the phase plot. So how many breakpoints we have? We have 3 breakpoints in the middle and 3 breakpoints on the right. They are 10 to the power of -3, 10 to the power of -2, 10 to the power of -1. Then we got 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. We need to analyze what happened at each band on this axis, like between the interval of 2 breakpoints. So from 0 to 10 to the power of -3, what happens? The constant give you a 90 decibel in the magnitude, and the G2 give you 0 decibel, and G3 also give you 0 decibel. So that is 90 minus plus 0 and plus 0. So at in the first band, you got 90 decibel. On the second interval, from 10 to the power of -3 to 10 to the power of -2, what happens? It's still 90, right? Like the first plot is still 90, and the second plot is still 0, and third plot is still 0. So here you still got 90 decibels. And then what happens starting from the 10 to the power of -2? The first plot is constant, and on the second plot, it's 10 to the power of -2 is far away in the left. So yes, questions.
What about 10 to the 0? Do we care about that?
Yeah, that's a good question. Like some student asked the same question last year. And we don't care about that because that is not a breakpoint. We only have breakpoints at 10 to the power of 1, 2, 3 and -1, 2, 3. That is the 6 breakpoints we have. Why we don't care about the 10 to the power of 0? Because nothing changes there. From above it and from below it, nothing changes. The trend, everything will be the same, remain the same, so we ignore it. Yes, great. That's a good question, and let's move on. From 10 to the power of -2 to 10 to the power of -1, what happens? The first plot remains the constant. The second plot also remains constant because the breakpoint is 10 to the power of 2. We are just at 10 to the power of -2 here. What changes is on the third plot. You got a slope going down. That is to say, you have a -20 decibel decreasing from 10 to the power of -2 to 10 to the power of -1. And this decreasing will keep going on until the middle plot start to increase. Like it increases as 20 decibels, and the third plot decreases as 20 decibels. So when they both are increasing and decreasing, these two things should cancel out. You should have a flat point. So what is a breakpoint when things cancel out? That is the 10 to the power of 2. When the middle plot is starting to grow, and the third plot is still going down, I'm sorry. Yeah, so we will keep having the -20 decibel decreasing until the breakpoint 10 to the power of 2. That is 90 plus 4 decibel of 20 degrees, 4 decades of 20 decibels of decreasing. That is 10 decibel. So at 10 to the power of 2, you got the magnitude of 10 decibel. Then the decreasing stops. You have no decreasing, you have no increasing. You got another flat line. So you will keep having the 10 decibels when the omega grows super large. So any question about the analysis of the magnitude? Great, let's move on to the phase. The breakpoints are still the same, so I just plot them at the same position, but I don't mark them. You should know, at the same position, you have the same breakpoint. At the beginning, when omega is very small, you have all the phase to be 0 degrees. So at the beginning, it's 0 degree. Then when you go to 10 to the power of -3, what happens? You have the phase of the third plot, the G3, going down at 45 degrees per decade. So from here, you got minus 45 degrees per decade. And you keep have this decreasing until what time you stop it? Until when the second plot started to increase. And they are increasing and decreasing at the same speed. So at that point, they will cancel out. What is that point? That point is 10 to the power of 1. So until this point, you will get, you will have minus 45 degree of decreasing. Wait, 10 to the power of -1. I'm sorry, this is wrong. Yeah, you discovered it very fast. Yes, until 10 to the power of -1, you keep decreasing and you stop. So how many degrees you decrease during this period? You decrease for 2 decades, so it is minus 90 degrees now at 10 to the power of -1. Then what happens starting from 10 to the power of -1? You have a flat curve because something is increasing and something is decreasing. Until the increasing stop. Oh, I'm sorry. It's not a flat curve because at 10 to the power of -1 on G3 it stopped decreasing, and but on G2 it keep decrease. So it will start increasing at 45 degrees per decade. So it is increasing 45 degrees per decade. Until 10 to the power of 3. At that time, the middle plot stop, and wait a second. Middle plot stop, and you got a flat line. Yes, what's your question, please?
Doesn't the increase start at 10 to the power of 1 instead of 10 to the power of -1?
Yes, you're right. My bad, yes. The increase start at 10 to the power of 1. So the increase start here. And between 10 to the power of -1 and 10 to the power of 1, you got a flat line because they cancel out. Yes, you're right. And those increase ends until 10 to the power of 3 when both plots are flat lines now. Okay, then we have finished the analysis of the magnitude and the phase. We need to just plot them into the final Bode plot. Let's plot the breakpoint first. 10 to the power of -3, 10 to the power of -2, 10 to the power of -1, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. And for the y-axis, we start decreasing from 90 decibel. So let's make it 90, 60, 30. And finally, we decrease to 10 decibel, if you remember from the last slide. So we plot as 10 here. We have a flat line until 10 to the power of minus 2. Then we keep decreasing for 40 decibel, for 20 decibel per decade. Until 10 to the power of 2, we got to the 10 decibel. And here's a slope between these two. So this should be the magnitude plot of this transfer function. For the phase plot, according to our previous analysis, it will be a flat line at the beginning, then it decreases. Then from 10 to the minus 1 to 10 to the 1, you will have a flat line because things are decreasing and increasing, they cancel out. After that, you got an increasing curve, increasing line until it goes back to a flat line. So make the y-axis minus 45 degrees and minus 90 degrees because that's what's happening every decibel. You have a flat line until 10 to the power of minus 3. Then you decrease by 45 degrees per decade until 10 to the power of minus 1. So here's a slope. Then you keep this degree for 2 decades until 10 to the power of 1. This is flat. Then you increase for 45 degrees per decade until 10 to the power of 3. And after that, it is still a flat line. Nothing is changing. So here we have the magnitude plot and the phase plot of this transfer function. So this example shows you how to draw the Bode plot of a complicated transfer function. Basically, you just factorize them into those basic transfer function. You plot the Bode plot of each basic transfer function. Then you kind of add them together, and you draw the omega axis of the phase and magnitude, and you analyze what's happening on each band on that omega axis. After your analysis, you draw the final Bode plot according to this analysis. That's the trick of plotting the Bode plot of a complicated transfer function. All right, any questions? Great. So then we finish the lecture of Bode plots.
Could you go back to the graph, please?
Oh, wait, sorry. This graph?
Yes.
Okay. Okay. It's 3:40 p.m. now. We still have a lot of time. Okay, cool. We still have a lot of time to go to the Nyquist plot. Everybody finish on this? Can I go to the Nyquist plot? Cool. So I can do a bit faster than what Professor Bridgman did last year. Since last year, a lot of students are asking a lot of questions, but this year, I got very few questions. The Nyquist plot. The first question is why we need the Nyquist plot. We already got the Bode plot. Why we need the Bode plot? Because we want to know what will be the response of the system when you give it input with some frequency and some magnitude. And why we need the Nyquist plot? Because we want to analyze the stability of some open loop system and closed loop system, especially the closed loop system. And to analyze the stability, Bode plot is not enough. It just tells you what will be the output according to the input. Previously, we learned another tool to analyze the stability. Do any student have memory about this? Oh, that's great. That's great. Rose Herbert's table, yeah. We use that table to analyze the stability. But you need to do a lot of calculations for the use Herbert's table, and it's just not concrete enough. I want the plot to see what's happening and to analyze the stability. So that's why we need the Nyquist plot. So let's first talk about the open loop Bibel stability analysis, bounded input, bounded output. We have an open loop system. The block diagram will be, here is a controller. Oh, sorry, C, not G. And oh, what happened? Okay, fine. We have the controller, and we have the input reference trajectory, RS. The output of the controller is the US. And in every system, you always have a disturbance, DS. For example, Lila always said, no actuator is perfect. So, yes, please.
Sorry, what are the two arrows on either side of C of S labeled?
The input is the RS, the reference trajectory. The output is the US, is the output signal of the controller. Yeah, so you have the output signal and you always have a disturbance. Lila always says no actuator is perfect. Sometimes the actuator breaks, you have a disturbance. Then the output signal of the controller and the disturbance add together. You input it into the plant, PS. Yes, please.
I have a question about Nyquist plots. So in general, how do they differ from Bode plots? Bode plots give us the magnitude and phase of the overall transfer function for different frequencies.
Yeah.
How does this differ in terms of stability analysis?
In terms of what analysis?
Like, what other information does it give us? How does that?
Yes, we're going to talk about the Nyquist plot hopefully in the later time of this lecture. And the difference is the Nyquist plot is used to see, like, suppose we know the number of poles, but we don't know the number of zeros. And we know how many poles are inside the curves of the Nyquist plot. According to the numbers of poles inside the Nyquist plot and the zeros we know, we can calculate how many poles in that system. So like for a system, we cannot have the transfer function. We don't know how many poles there is. We use Nyquist plot to analyze how many poles it has. When we know how many poles it has, we can furthermore analyze the stability of the system. But I think I don't have enough time to finish the entire Nyquist plot content today. So Lily will finish the later half part. I will give you a start, like at the beginning, introduction of how we introduce Nyquist plot, why we need it. Okay, let's keep going. We have the plant. The transfer function is PS, and the plant output. I'm sorry about that. Output the YS, which is our observation of the plant. Okay, great. Now we need to calculate the transfer function of these four things. The first thing is the transfer function of the reference trajectory to the plant output, GRY. What should it be? According to the block diagram, GRYS should be the transfer function of the plant multiply the transfer function of the controller. Any question about this transfer function? No, great. Then we need to know what is the transfer function of the reference trajectory to the control output, GRUS. So that is U over R. What should it be? It is CS. It is just the transfer function of the controller. Yes, please. What's your question?
So labeling the different signals up there, you called US control input, and then here you're saying this is the transfer function for reference to control output. So what's the difference between control output and control input?
US, I call it control input. That's a good question. Lila writes control input here in the slides in last year, but I think the US is the control output. That is the output of the controller. That is the control output. The control input should be the RS, the reference trajectories. So that's a good question, and I don't think that's my fault. That's Lila's fault. And US should be the control output. Thanks a lot. That's my understanding. But if Professor Bridgman has some different understanding, you should listen to her opinion, not mine. Okay, that's my understanding. US should be control output. Okay, great. Then we need to know the transfer function of GDY. That is the disturbance to the plant output. So that is Y over D. Which should be the PS. Because when you want to know the transfer function of Y over D, you suppose the R equals to 0. That's what you do. When R equals to 0, the U is 0. And the only input to the plant is the D, please.
So this function is only applicable when we don't have a reference signal. It's only disturbance.
Yes, but I don't think this function is only useful when you don't have reference trajectories. It tells you what's the influence of the disturbance to my plant output.
So when we have a reference signal and that does create a U of S output, can we just add that U of S to this to get the overall behavior?
As long as the transfer function of the plant PS is linear, I think you can. And we always suppose everything is linear here. Like Lila said in the third or fourth course, we can only analyze linear systems. So that's why she does a lot of Taylor theorem stuff to linearize the system. Yes, that's a good question. Thank you. And the last thing we need to do is the GDU is the transfer function from disturbance to control output. So in this case, we suppose reference equals to 0, and then U equals to control, the CS, the transfer function of the controller, times 0, which is 0. So what does it mean when we say a transfer function is 0? It means the disturbance has nothing to do with the controller output. It's an open loop system. I don't care what the disturbance is. I just do according to my reference trajectories. Okay, great. And What makes all 4 transfer functions stable? When we have all these 4 transfer functions listed here, what makes them all stable? The first thing is we need the CS, which is transfer function of the controller, must be stable. And the second criteria is I need the transfer function of the plant must be stable. Okay, and last year a student asking a question like, he's saying the whole point of control theory is when the plant is not stable, we are designing some controller to make it stable. Now you are requiring the plant to be stable. What do you mean? So the answer is here. This is an open loop system. So if you need all the transfer functions stable, you have to have a stable plant. When the plant is not stable, do the closed loop. Yes. The perform stability analysis is, the first thing is we need to perform stability analysis on the plant according to our conclusion about. The second thing is perform the stability analysis on the controller. Because our care about is the CS and the PS. The special transfer function of the open loop open loop system is GRY, which is PIS times CS. All right, please.
Say in the disturbance to control output.
What?
What does it say U equals something times 0?
You can you come up and
In the disturbance to control output.
yeah, U equals CS times 0. Yeah. Oh, I'm sorry about the writing. Yeah, please.
Could you explain the disturbance to control output transfer function again?
What?
Can you explain the disturbance to control output again?
Yeah,
What
yeah.
the output and the input to the transfer function will be?
The output of the transfer function is U, and the input is the D, disturbance. The output is US, input is DS.
But D doesn't go into the controller.
Yes, that's why the transfer function is 0.
So we say disturbance to controller output, but it's just 0 to controller output.
Yes, we say the transfer function of disturbance to controller output is 0, and that means the disturbance doesn't influence the controller output at all. Yes. Any other questions? Can I move on to the closed loop Bode stability analysis? Great. After the open loop analysis, which is a simpler one, this thing will be a little bit more complicated. The closed loop Bode stability analysis. Let's first draw the block diagram of the closed loop system. We have a plant here. The transfer function is PS. And the plant output is the YS. This plant output goes down, and there is a reference trajectory, RS. The plant output minus the reference trajectory is the ERO, ES. I want the output to be reference, but it is Y, it is not reference. What's the ERO between these two things? Then the ERO goes into the controller, the CS. it takes in the ERO and output a control signal, which is the US. And the control signal goes up. Like we said, no system is perfect. You always have disturbance, DS. So the disturbance is minus by the control signal, and this thing is input to the plant. That is the block diagram of the closed loop system. So we have Y equals to P D minus U equals to P D. What is U? U is the control system times the ERO. Yes, please. Do you have questions? Okay. I heard you saying questions. So. Okay, fine. It is equals to P times D minus C. What is the ERO? The ERO is the Y minus reference system, reference trajectory. Then we need to assume that C, the transfer function of the controller, and P, the transfer function of the plant, are linear. We always need to assume them to be linear. If they're not, do the Taylor theorem and linearize them. And we get the Y equals to PD minus PCY plus PCR. All right, then we want to isolate Y. So we move everything with Y to the left-hand side. Y plus PC times Y equals to PD plus CR. To isolate Y, we need to make another assumption, that is 1 plus PC is invertible. I think you have done these two assumptions a million times in your previous homework. So Y equals to 1 plus PC to the power of minus 1 P D plus CR. Like, pay attention to the 1 plus PC to the power of minus 1. This is going to appear again and again in the future equations. We need to get the force transfer function that we have in the previous open loop system. So for the reference to the plant output, we suppose disturbance is 0. Then we have Y equals to 1 plus PC to the power of minus 1 PCR. So the transfer function GRY equals to Y divided by R equals to 1 plus PC to the power of minus 1 times PC. Okay, now we go to the transfer function of the reference trajectory to the control output. We have D equals to 0, and U equals to Y minus R equals to, what is Y? C, I need to write this thing smaller. This is the most complicated one. If you write it that large, you cannot fit it in. Any question about this equation? How do we get that? This is a very complicated part. Like last year, Lila did this and she did it wrong. And after 5 minutes, some other student figure out which part is wrong. I think, yes, please.
So you're supposed to multiply y minus r by c.
What?
Are you supposed to multiply the y minus r by c?
Y minus r by c. That's a good point. Yes, you're right. C. I missed a c here. Yes, your question? Oh, the same question, right? Okay. Yeah. So this you got this equation because d equals to 0. Yes, your question.
PCR minus y.
PCR minus r, I think.
PCR minus.
Because you just copy the minus r from the previous part to the next part. You plug in the y there, but the d is equal to 0, so you don't need to write the d. Okay, great. The next step is a little tricky. Then you got u equals to c. You pull out the 1 plus pc to the power of minus 1. Pull this thing out. So then you get inside here is PCR. And when you pull it out, you got and 1 plus pc times r here. Can you understand this step? You pull out 1 plus pc minus to the power of minus 1. But the last part is the r. You don't have that thing. So you have to multiply back 1 plus pc to the power of 1. Everybody okay with this step? Great. Then you take a look at what's inside these things. You find that this is a PCR and this is another PCR. When you open that thing, they cancel out, right? So u equals to minus c times 1 plus pc to the power of minus 1. Because you only got a minus 1 inside. You divided by r, I'm sorry. Is this step okay? Any questions? Okay, great. I think this is the most complicated one. The remaining two will be much easier. And so the GDY equals to y over d. And you plug in the y with r equals to 0. You can have p what's happening to this slide? Over 1 plus pc. Because r equals to 0 here. We only analyze the influence of the disturbance, so the reference is 0. then you plug in y, you got this result. For the last one, u equals to c y minus r. And r equals to 0, so it is cy. So gdu equals to u over d equals to cy over d, which is cp over 1 plus pc. When you just plug in the y, and you make the r equals to 0. Okay, we got all the transfer functions of.
Sorry, could you wait for a minute for?
Yeah, please.
to write the last part?
No problem. Yes, please. Basically, the rule says when you analyze the influence of one signal, you make the other signal to be 0. Yes, please.
Are is GRY the same thing as GDU?
Yes, but not entirely yes, because if you can look at the denominator, GRY is P times C. But the GDU is C times P. But when you have only single input, single output system, they are the same. But when you have multi-input, multi-output, when these two metrics are not commutable, they are different. Like you have some non-linear stuff and you have multi-input, multi-output, that would be not the same. But for simple cases, they are the same. Yes, because some students asked the same question last year. Okay. Everybody finished on these 4 transfer functions? Great, and now we need to analyze the stability. How to analyze the stability? We need to analyze how to make it stable. We need to make the roots of the denominators outside the right half plane. If you have any root in the right half plane, it's not stable. So let's suppose C equals to denominator of C over denominator of C. The plane's transfer function equals denominator of plane over denominator of plane. And if we make these marks, the denominator and denominator stuff, what we have about 1 plus PC, 1 over 1 plus PC. Because if you pay attention to all these transfer functions, we always have this thing, 1 plus PC to the power of minus 1. What is that? 1 plus PC equals to 1 over 1 plus P and C dP dC. To make it tidier, we got dP dC over dP dC plus NP and C. You just multiply both the numerator and denominator with dP dC. That's the 1 over 1 plus PC in the form we want. So for the GRY, if we plug in the form of 1 over 1 plus PC, we have dP, I'm sorry. Over dP DC plus MP NC times what? Times PC. What is PC? PC is MP NC over dP dC. Then you can notice that the dP dC cancel out. What happened? I just cannot write that cancel out. Okay, great. And for the GRU, you have dP dC over dP dC plus NP NC times minus C. What is minus C? That is minus NC dC. Then you find that this dC cancel out with this dC here. For the G dy, we have dP dC C times NP dP. Because in the denominator you have the P. Then you find that this dP cancel out with this dP. For the GDU, we have dP dC over dP C plus NP NC times CP. What is CP? NC dC times NP Sorry. I'm waiting for this computer. NPNC. Oh. This computer is causing me so much trouble in this lecture. Sorry about that. And you cancel out the numerator and denominator like this. Then we observe this for transfer function, what we have. We can see the denominator here is dP dC plus NP NC, just like the denominator here, and the denominator here, and the denominator here. These four are just the same. Everything else on that denominator cancels out. So here is our conclusion. To check the stability of the closed loop system, we just need to check whether dP/dC plus NP/NC has roots in the right-hand side plane. Okay, fine. Any question about this? So why is closed loop analysis? Yes, please.
So we derived the 1 plus PC part had a denominator of dpdc plus mpnc, right?
Yeah.
That we then use to cancel the others. Isn't the 1 over 1 plus PC coming from the open loop part?
The one is the question is
The PC there is already seen in the open loop part.
yes, the PC is seeing the open loop part, but the 1 plus PC, the 1 is caused by the closed loop. I think that's my understanding. I'm waiting for this computer to transfer to the next slide. Okay. Why is closed loop analysis much harder than open loop? For the open loop system, you just need to do two things. You check the roots of dp, and you check the roots of dc. Then you're done. The analysis is done. For the closed loop analysis, you need to check the roots of dpdc plus mpnc. So the order of dp dc plus mp and c equals to the order of dp plus order of dc. Why this equation stands? Because we assume that the transfer function of the plants and the controller are strictly proper. So we don't need to consider about the denominator. That thing will be smaller. And this makes finding roots of dpdc plus mpnc much harder. The dream is we want to analyze the closed loop stability using only the open loop transfer function. And the crucial observation here is that the roots of dpdc plus mpnc are the poles of 1 plus pc to the power of -1. Or you can see the zeros of 1 plus pc. So the missing tool here is we need a pole detector. To analyze the stability, we need to analyze the roots of this dpdc plus mpnc.